So in this presentation, I will summarize the results and the works carried out in OLEUM project concerning the reinforcing of quality control. From a global perspective, any action to improve quality and to improve the control of quality requires, on one hand, the improvement of the panel test to obtain a quantitative panel test, and also including the formulation of reference materials. And also, it also involves the development of a methodology for the freshness assessment control. The improvement of quality also involves the development of methods for determining the phenols in relation with supporting the health claim application, and also the determination of volatile compounds to support the daily work of a panel test. Starting with the panel test, in OLEUM project, we developed a decision tree. This decision tree, you can see in the slide, was adopted for the statistical processing of the sensory results that are provided by different panels. And sometimes, as you know, sometimes you can obtain some kind of disagreement. We defined two types of errors, one of them related with the category, and another kind of error was related with the median of effect or the fruitiness. In fact, this decision tree was put in practice with more than 300 samples. Many of them were borderline samples between different categories, so they were covering all kinds of categories, and they were analyzed by 6 sensory panels. We observed an agreement of 86%, but it was interesting to see that this agreement rose to a percentage of 98 when a formative reassessment was implemented in the panels. So highlighting the importance of the training in the panels and also highlighting the importance of developing reference materials. In fact, in OLEUM project, we formulated 2 kinds of reference materials, one of them on winey vinegar effect, and the other one related with rancid effect. Here in the slide, you can see the volatile compounds that were selected for formulating these reference materials, and they were diluted in an odorless matrix. In this work, we also designed a flow chart to develop reference materials for winey or for rancid, but also for any other kinds of reference material that we want to develop in the future. This flowchart consisted of 3 phases. One of the phases are related with the collection of information, the background information from previous work. The second one is the building process for optimizing the concentration of each one of the volatiles. And the third one is the validation process. The objective is to obtain a reference material that is reproducible in their production, and it is also accessible to be used in an easy way in the training and monitoring of panelists and also of panels. In the validation phase, we determine the odor threshold, working with 6 sensory panels. Here you see the results. And surely tomorrow, Professor Alessandra Bentini is going to provide more details about this. In this validation phase, also, the shelf life was evaluated in a period of 6 months, in which 6 sensory panels were evaluating the median of effect of these reference materials. We didn't observe any significant variation in these 6 months. Also, for supporting the sensory panel, different screening methods were tested. Some of them related with SPME GCMS with an untargeted approach, of flash gas chromatography electronic nodes, of gas chromatography ion mobility spectrometry, or also NMR. Here you see the classification rates. Most of them were in the range of 80–90%. For example, one of the screening methods that was selected for the validation phase at the end of the project is the method based on SPME GCMS with an untargeted approach, in which 2 binary PLS models were applied. In this case, the classification rate was 84% when this method was applied together with panel test. That means an error of 50% or less. It's important to highlight in this method that it is working with two-step classification, but also defining an uncertainty zone, as you can see in the slide. Also, in OLEUM project, we developed a method for the identification and quantification of each one of the volatile compounds. We can say that this is a targeted approach. In this work, we developed two protocols, one for mass spectrometry and the other one for FID. And we also developed an additional protocol for building the calibration curves, together with an Excel file for the data processing. We developed this protocol for the calibration curve building because we identified that this was one of the error sources when different labs were comparing the results. In fact, in this work, here in the slide, you can see the general scheme. In a first phase, we identified all possible error sources. Once we identified the errors, we drafted a joint protocol, one for FID, another for mass spectrometry. And when these joint protocols, we calculated the limits and ranges of concentrations, and we carry out a within OLEUM validation. That's it. It's a validation with the OLEUM partners. After all this work, we proceeded to the external validation for an interlab validation with labs that they were not OLEUM partners. This method was based on 18 volatile compounds that were selected because they were markers, or they were responsible for different sensory effects, and some of them also responsible for positive attributes. We recently published the results of the validation within OLEUM with the OLEUM partners. Here in the slide, you can see the different partners for FID and mass spectrometry. And we are now finishing another publication with mass spectrometry. As you can see, we evaluated repeatability, reproducibility, linearity, etc. But it's important to note that we were talking about 18 volatile compounds, 2 kinds of detectors, FID and mass spectrometry, 3 possible quantification methods, because we tested different ways of quantifying the compounds. I hope to give some details tomorrow. And also 6 quality parameters, as I said, the linearity, repeatability, etc. So that means actually 648 values. It's very complex to summarize this in a slide, but here you see the mean and the different ranges. There are, of course, some particular cases with maximum values that they were related, for example, because some samples were below the limit of quantification. Also, it's important, and it is one of the phases of the working OLEUM project, the calculation of the limits and the concentration ranges for each one of the categories, extra virgin, virgin, and lampante. In this case, it was important to consider a reliable quantification data, and that's why we worked with an interlab perspective. That means that we calculated these limits with different labs in order to include the error within the limits. And also, it's important to have a representative samples. So we work with 60 samples covering all possible kinds of concentrations for each one of the volatile compounds. Also, with the aim of developing a methodology for controlling or for assessing the freshness of virgin olive oil, a specific work was carried out within OLEUM project that was coordinated by Professor Mauricio Servilli. He's going also to present the results tomorrow. So in this work, a prediction model was obtained from a large of analytical data set, including many kinds of samples, and also many kinds of analytical information. All these samples were subjected to different conditions of storage, mainly using temperature and light, dark. In this period, legal parameters were evaluated together with hydrophilic phenols, alpha tocopherols, volatile compounds, and fatty acid composition. So the prediction model was validated internally and also externally. And tomorrow, I'm sure that Professor Servilli is going to present some insights of this methodology. This slide shows the homepage of the software that was developed. And also, a specific work was carried out for developing a methodology for analyzing the phenols that are relevant for the health claim. In other words, the objective was to obtain a methodology for analyzing the phenols for supporting the health claim application. So this work was coordinated by Professor Maria Simidou. Tomorrow, Professor Nikolaos Nenadis is also going to provide some insights about this specific work. So the work, as you can see in the slide, this is a nice timeline of all the work. Started with a collection of all the information from the different analytical possibilities available. And also it is important to highlight that a consensus was obtained or was reached in the case of which are the phenols relevant to the health claim. The work continued with the development of a protocol for the determination of total hydrotyrosol and tyrosol, and the harmonization and standardization of this protocol. This protocol resulted in a methodology based on ultra HPLC DAD for the analysis of hydrotyrosol and tyrosol. And this method was internally validated, was in-house validated, and was selected for the Interlab validation at the end of the project. So I think some results are going to be presented tomorrow. It's also interesting to highlight that other methods were tested. For example, one related with fluorescence spectroscopy that was developed by Smart Essays, and also other methodologies, alternative methodologies, were supporting the work during all this period. For example, NMR was used, for example, for the sampling, for obtaining all different kinds of sample with different ranges of concentration of phenols. This specific work released a high number of publications. Here you can see some of them. I invited you also to have a look to these publications. Many of them are in open access, so it's easy to reach to the details of the validation, for example, and also the details about the analytical properties of these methodologies. So I hope to provide an insight of all the works. It's difficult to do it in a short time, but as I said during the presentation, some of the publications are already available, and tomorrow so the methods that I referred to in these slides are going to be presented. So we will have more time to understand the methodologies, the importance, and also some analytical information resulted from the Interlab validation.